In 1878, Somerset was a quiet settlement, a piece of natural paradise at the western end of Bermuda. This tranquility was, however, broken by a serious crime that shocked the local community and later contributed to reforms in the island's police system. The unusual circumstances surrounding its discovery also attracted scientific interest. As a result, the naturalist Henry Nottidge Moseley, known for his participation in the Challenger expedition, wrote to the journal Nature to describe what he termed a remarkable discovery of a murder in Bermuda. For a time, the crime that occurred in Somerset remained wrapped in mystery. According to reports of the period, a handsome and well-regarded woman, the wife of a fisherman, disappeared suddenly and entirely from sight. Suspicion soon fell upon her husband, who had a known history of violence toward her, though he claimed she had left him, taking his money. With no trace of the missing woman, the crime risked remaining undetected. Friends of the victim were unconvinced and began searching on their own. During this effort, some boatmen noticed something unusual in the Long Bay Channel, a long, distinct streak of calm water, while the surrounding sea was lightly rippled by the wind. A connection to the woman's disappearance was immediately suspected. A search was soon conducted at that location, and as the area beneath the calm waters was dragged, skeletal remains were recovered. The body had been weighted and held on the seabed, and it was identified as that of the missing woman. The husband was arrested, later tried, and found guilty. For Moseley, however, the most compelling question lay beyond the crime itself. He was struck by the phenomenon that had revealed it. How could a decaying body beneath the surface produce a visible streak of calm water above? To his knowledge, such an effect had never been documented. In his letter to Nature, he wrote,
"The case seems to be an exceedingly interesting one. The calm is not mentioned in any book on medical jurisprudence that I have, and the doctors seem not to have had experience of such an occurrence."
But Moseley was wrong. Over a century earlier, another man of science had already described the phenomenon. His name was Benjamin Franklin. In 1757, Benjamin Franklin was sent by the Pennsylvania Assembly to England to negotiate over taxation. During the voyage, while sailing with a fleet of ships, he observed that the wakes of some vessels were remarkably smooth, even though the surrounding sea was choppy and ruffled by the wind. He was struck by how certain ships left flat, calm trails behind them, while others produced the usual turbulent wake. When Franklin asked the captain about this phenomenon, the captain was amused by his surprise, explaining that it was well known the smoothing effect was caused by oil released into the water, most likely from the cooks, who had just emptied their greasy wash water into the sea. Fascinated by the phenomenon, Franklin conducted the first controlled experiments on ponds and lakes. He published his findings in a scientific paper, noting that sailors had known about this effect for generations. Seamen called it storm oil, and stories circulated of captains pouring oil onto raging seas to quiet the waves during violent storms. But Franklin didn't just study the phenomenon, he played with it. Known for his wit, he had a hollow walking stick made to hold a small amount of olive oil. With a subtle press on the handle, oil would seep from the tip, letting Franklin astonish his friends by appearing to magically calm choppy waters. What could a murder investigation, sailors pouring oil on stormy seas, and experiments by Benjamin Franklin possibly have in common? The answer lies in a subtle but powerful property of liquids: surface tension. Before we dive into this strange mystery, take a second to help the channel grow. If you enjoy uncovering surprising connections like this, hit the like button and subscribe. All right, now let's uncover what these seemingly unrelated stories reveal about the mysterious behavior of water surfaces. To understand it, we need to look at how waves are born. When wind blows over calm water, it transfers energy across the air-water interface. At first, this energy doesn't create rolling waves. Instead, it produces tiny ripples called capillary waves. The dominant restoring force is surface tension, and gravity plays a minor role. These ripples, though small, roughen the surface, enabling the wind to couple more effectively with the water and transfer additional energy. As the waves increase in size, gravity gradually becomes the dominant restoring force, and familiar wind-driven waves begin to form. This creates a feedback loop. Wind creates ripples, ripples increase surface roughness, roughness enhances energy transfer, waves grow. The formation of those initial ripples is dominated by surface tension, which acts as a restorative force to the deformation produced by the wind. But what is surface tension? Where does it come from? Well, surface tension is a way that liquids resist an increase in their surface area. Water molecules are polar, like electric dipoles. Therefore, they attract each other. When molecules are in the middle of a liquid, they are attracted by all the other molecules. But molecules at the surface are imbalanced. There are only molecules below and beside them, which produces a net force attracting them to the interior of the liquid. Let's imagine what happens if one molecule is pulled down to the interior of the liquid, leaving a momentary hole on the water surface. The molecules on the sides of the gap would then attract each other to get as close as possible, trying to close the gap. This generates a force that acts tangentially to the surface of the water, which is the origin of surface tension. The surface tension makes water behave like it has an invisible elastic film on its surface. Because of the surface tension, light objects like a paperclip, which are denser than the water, can actually float on it if they are put carefully on its surface. Some insects can walk on the water's surface because of it. It is also because of surface tension that drops tend to be spherical, and they also help produce waves together with the gravitational force. But why does pouring oil on stormy seas calm the water? And why would a decaying body create a smooth, wave-free streak on the surface above it? To answer that, we need to understand surfactants. The most familiar surfactant is soap. A soap molecule has two very different parts: a polar head that loves water and a long nonpolar tail that avoids it. Because of this structure, surfactants naturally gather at the water surface, with their heads submerged and their tails sticking out. Surfactants weaken the attraction between water molecules at the surface. Natural oils like fish oil or olive oil are weak surfactants, but they contain free fatty acids and partially hydrolyzed fats, which are much stronger surfactants. A decaying body releases similar compounds, which explains why it can create the same calming effect observed by sailors centuries ago. Lower surface tension already reduces the formation of tiny capillary waves. But scientists believe an even more important mechanism is at work: the Marangoni effect. In this experiment, pepper powder is sprinkled across the surface of the water to make otherwise invisible surface flows visible. When a cotton swab dipped in soap touches the water, something remarkable happens. The soap lowers the surface tension at the point of contact, creating a difference in surface tension between that spot and the surrounding water. The liquid immediately flows away from the area of lower surface tension toward areas of higher surface tension. This phenomenon is known as the Marangoni effect. When surfactants spread across a water surface, waves create tiny variations in surfactant concentration. These molecules temporarily accumulate at the crests of waves, where they reduce the surface tension locally. This imbalance generates a flow down the sides of the wave, counteracting its growth. Without capillary waves, the water surface becomes smoother. When the surface is smoother, the wind has a harder time transferring energy into the water. This is why even a molecularly thin layer of oil can calm ripples over large areas of the sea. Additional mechanisms may also contribute to this calming effect, such as viscous energy dissipation at the water surface. If you'd like to explore this topic further, check out the article Surfactants on Troubled Waters and the related video on the Action Lab channel. Links are in the description. Thank you all so much for watching. Your support means everything. Don't forget to like, subscribe, and turn on notifications so you never miss a video. Catch you in the next one.